Assalamu alaikum students, my name is Saqib Ejaz and I'm your instructor for the course of Electromagnetic Field Theory, EMT. Today we will discuss about electrical potential. From our discussion in the preceding sections, the electrical field intensity, which we denoted that it as E due to a charge distribution, can be obtained from the Coulomb's law in general or from Gauss's law when the charge distribution is symmetric. Another way of obtaining E, electrical field intensity, is from the electrical scalar potential, which we denoted as V, to be defined in this section. In a sense, this way of finding E is easier because it is easier to handle scalars than vectors. When we talk about electrical potential, we suppose we wish to move a point charge Q from a point A to point B in an electrical field E. The figure is shown in the next slide. So from Coulomb's law, the force on Q is F is equal to Q into E, so that the work done in displacing the charge by dl is dl is equal to minus F dot dl is equal to minus QE dot dl. The negative sign indicates that the work is done by the field. Thus, the total work done or the potential energy required in moving Q from A to B is W is equal to minus Q into E dot dl. By dividing W by Q in equation 4.59 gives the potential energy per unit charge. This quantity, denoted by VAB, is known as the potential difference between point A and B. So if we change the equation, VAB will be equals to W over Q is equals to minus from point A to B E dot dl. As we can see in the figure 4.18, the displacement of point charge Q in an electrical field, let's suppose we have point A and point B, the vector A and vector B, in an electrical field E on a line. So we can see dl is the resultant vector, and we have the radius R, RA and RB of all these vectors. So the electrical potential, also called the electrical field potential or the electrostatic potential, is the amount of electrical potential energy that a unitary point electrical charge would have if located at any point in a space, and it is equals to the work done by an external agent in carrying a unit of positive charge from the arbitrary chosen reference point excuse me, usually infinity, to the point without any acceleration. According to the theoretical electromagnetics, electrical potential is a scalar quantity denoted by V equals to the electrical potential energy of any charged particle at any location. It is measured in joules divided by the charge of the particles measured in coulombs. By dividing out the charge on the particle, a remainder is obtained that is a property of the electrical field itself. So this value can be calculated in either a static time invariant or a dynamic, which we call varying with time electrical field, at a specific time in a unit of joules per coulombs or volts. The electrical potential at infinity is assumed to be zero. A generalized electric scalar potential is also used in electrodynamics, which, when time is varying, electromagnetic fields are present, but this cannot be so simply calculated. The electrical potential and the magnetic vector potential together form a four vectors, so that the two kinds of potential are mixed under Lorentz transformation. So note that in determining VAB, A is the initial point while B is the final point. Like we started from A and going towards the point B. If VAB is negative, there is a loss in potential energy in moving charge Q from point A to point B. So this implies that the work is being done by the field. However, if VAB is positive. There is a gain in potential energy in the movement. An external agent performs the work. VAB is independent of the path taken, that to be shown in a little later. VAB is measured in joules per coulombs, commonly referred to as volts. So this figure is actually telling you about the electrical potential when we have a charged particle moving from point A to point B. Okay, let's continue with electrical potential. As an example, if E is an electrical field intensity in a figure 4.18 is due to a point charge Q located at the origin, then we know the basic formula for electrostatic field is E is equals to Q over 4 pi epsilon naught R squared with the unit vector AR. So equation number 4.60 becomes VAB is equals to minus RA towards RB Q over 4 pi epsilon naught R square AR with dot dr with the unit vector AR. So if we simplify that, we will get VAB is equals to VB minus VA. As we know the basic formula for electrostatic field intensity, which we have studied in the previous lectures. So where VB and VA are the potentials or absolute potentials at B and A respectively. Thus the potential difference VAB may be regarded as the potential at B with reference to A. In problems involving point charges, it is customary to choose infinity as reference. That is, we assume the potential at infinity is 0. Thus, if VA is equals to 0 as RA approaches to infinity in equation 4.62, the potential at any point RB approaches to R due to a point charge Q located at the origin is. So V is equals to Q over 4 pi epsilon naught R. Note from the equation 4.62a that because E points in the radial direction at any contribution from a displacement in the theta or phi direction is ripped out by the dot product E dot dl, which is equals to E cos of theta dl or E dr. Hence the potential difference VAB is independent of the path as asserted earlier. The potential at any point is the potential difference between that point and a chosen point at which the potential is 0. In other words, we can say by assuming 0 potential at infinity, the potential at a distance r from the point charge is the work done per unit charge by an external agent in the transferring a test charge from infinity to that point. Thus, V is equals to minus E infinity towards r E dot dl. So if the point charge Q in equation 4.63 is not located at the origin but at a point whose position vector is r dash, the potential across a V into x, y and z or simply V into r at r becomes VR is equal to Q over 4 pi epsilon naught r minus r dash. We have considered the electrical potential due to a point charge. The same basic ideas apply to other types of charge distribution like line charge distribution and surface charge distribution and volume charge distribution, because any charge distribution can be regarded as consisting of point charges. The superposition principle, which is applied to electrical field, applies to potential as well. Like we have applied if we have more than one field, one vectors and one points, we can say charge particles, and we have to find electrical field intensity on those points. So we can add them by applying superposition principle. So in this electrical potential case, we can apply a superposition principle to a potential as well. So we can say VR is equal to Q over 4 pi epsilon naught R minus R1 and plus Q2 over 4 pi epsilon naught R minus R2 plus so on Qn over 4 pi epsilon naught R minus Rn. Right? So we can have that summation formula, summation sign for all the nth term. Okay. For continuous charge distribution, we replace Qk in equation 4.66 with charge element ρl dl, ρs ds or ρv dv. This is for other charge distributions. As we have discussed, the line charge, the surface charge and the volume charge. And the summation becomes an integration. So the potentials at R becomes this. Becomes in the following equation 4.67, 4.68 and 4.69 by line charge, surface charge and volume charge respectively, where the primed coordinates are used customarily to denote source point location and the unprimed coordinates refer to field point, the point at which V is to be determined. So basically we have to remember the charge distribution of line charge, surface charge and volume charge, and then we apply the potentials across those distributions and we can get the formula. We recall that in obtaining equation number 4.63 to 4.69, the zero potential point has been chosen arbitrarily to be at infinity. If any other point is chosen as reference, equation 4.65 for example becomes, so that means that if we choose any other reference point, then we can say we can add a plus c, where c is a constant that is determined at the chosen point to point of reference. The same idea applies to equation 4.63 to 4.69. Okay, the point number 2, the potential at a point can be determined in two ways depending on whether the charge distribution or electrical field intensity is known. If the charge distribution is known, we use one of the equations 4.65 to 4.70 depending on the charge distribution. If E is known, we simply use V is equals to minus integral of E dot dl plus C. So here is again the same point. Let's move forward. The potential difference VAB can be found generally from VAB is equals to VB minus VA, and we put the equation and we get W over Q. Work done is divided by the charge. Let's have an example 4.10. The 2-point charges minus 4 microcoulombs and 5 microcoulombs are located at the points 2, minus 1, 3 and 0, 4 and minus 2 respectively. Find the potential at 1, 0, 1, assuming zero potential at infinity. So we'll have the simple case. This is a potential which are assuming a zero potential at infinity, and these are the point charges which are located on these points in a Cartesian coordinate system. So we know that the Q1 is the minus 4 microcoulombs and Q2 is 5 microcoulomb, and we know that we have to find the potential, and we can use superposition principle. Okay, so we can say VR is equal to Q1 over 4 pi epsilon naught R minus R1 plus Q2 over 4 pi epsilon naught R minus R2. We can find out R minus R1 by drawing the vector from the region to those locations which are given in the question, which is 2, minus 1 and 3 for minus 4 microcoulomb and 0, 4, minus 2 for 5 microcoulombs. So we can find out the R minus R, the magnitude of R2 minus R1. Okay, so when we find out this, we can find out the answers. So in this case, R minus R1 is equals to under root 6, and R minus R2 is equals to under root 26. So when we solve that, we can find out the answer. Just need to put all these values in the formula and we'll get the answer. That will be equals to minus 5.872 kilovolt. So this is the potential. There's another practice exercise 4.10. Let's solve this. If a point charge of 3 microcoulomb is located at the origin, in addition to the two charges of example 4.10, if we add the previous example 4.10, find the potential at minus 152, and assuming V infinity is equals to 0. So there's another point charge 3 microcoulomb, okay, which is located at the origin, and two charged particles from the previous questions, so we have to find all that. So what we need to do is we use a superposition principle and apply that. Vr is equals to summation of k is equals to 1 is to 3. So we have three charged particles and we have c, because it is assuming it has on infinity. So when we put all the values, we can get r minus r1, r minus r2 and r minus r3, which is 46 under root, 18 under root and 30 under root. So we can find out, we combine all that, put in the formula and solve them, so we'll have the final value of electric potential, which is equals to 10.3 kilovolt. Okay, let's move forward, and we have the relationship between E and V, and we call that Maxwell's equation. That it actually simplify or justify Maxwell's equation. As shown in the previous section, the potential difference between point A and point B is independent of the path taken. Hence, VBA is equals to minus of VAB. That is, VBA plus VAB is equals to E dot dl, integral of E dot dl, which is equals to 0. This shows that the line integral of E along a closed path, as shown in figure 4.19, must be 0. Physically, this implies that no net work is done in moving a charge along a closed path in an electrostatic field. But, as you know, delta V is equals to partial V over partial x dx plus partial V over partial y dy plus partial V over partial z dz. So comparing these two expressions for dV, we can obtain Ex is equals to minus partial V over partial x, Ey is equals to minus partial V over partial y, Ez is equals to minus partial V over partial z. And thus this equation becomes E is equals to minus delta V. Because if we remember, delta was partial over partial x into ax plus partial over partial y, ay plus partial over partial z, az. That is, the electrical field intensity is the gradient of V. The negative sign shows that the direction of E is opposite to the direction in which V increases, and E is directed from the higher to a lower level of V. So this actually simplify and justify the Maxwell's. Let's solve another example, and here we have given electric potential. The value is V is equals to 10 over r square sine theta cos phi, and they have two parts. So part A says find the electrical flux density D at 2 pi by 2 and 0. We have already discussed about electrical flux density, and we have already discussed about the coordinate systems. So when we look at 2 and pi by 2, the pi by 2 tells you something. It shows an angle. Okay, so that it can be a spherical coordinate system or a cylindrical coordinate system, depending on the conditions. Okay, we'll see later. Calculate the work done in moving a 10 microcoulomb charge from point A to point B. The coordinates are given, which is 130 degrees and 120 degrees, 2, 4, 90 degrees and 60 degrees. So these points tells you which coordinate system we are talking about. So let's solve this example. Let's start with the part A. We know that from the electrical flux density, D is equals to epsilon naught E. For finding D, we must know the value of epsilon naught and E, but E is not given. We know the value of epsilon naught. So we have to find E, but E is equals to minus delta V. We have discussed about delta V just in the previous slide. If you recall that delta V is equals to partial V over partial R, AR, plus 1 over R, partial V over partial theta, A theta, plus 1 over R sine theta, partial V over partial phi, A phi. Because we are talking about spherical coordinate system, because we have the coordinates 2, pi by 2 and 0. So that shows R, theta and phi for spherical coordinate system. Okay, when we put the value of V, that is 10 over r square sine theta cos theta, in this equation, so we will get the final answer in the next slide. Okay, So let's continue this example 4.12 at 2 and pi by 2 and 0. So d will be equals to epsilon naught e, we know the value of epsilon naught, and e, we have all the equations and derived, and we put the values here. So in the end we find d, which is equals to 22.1 AR picocoulombs per meter square. Let's move forward towards point B. The work done can be found in two ways, using either E or V. So there are two methods for solving them. Both methods are important, so I will solve with both methods, and it's up to you which method do you use. W is equals to minus Q integral of E dot dl, or we can write it down as minus W over Q is equals to integral of E dot dl. And because the electrical field is conservative, the path of integration is immaterial. Hence, the work done in the moving Q from A point to point B is the same as that in moving Q from A to A dash, from A dash to B dash, and from B dash to B, where A, which has coordinates 130 degrees and 120 degrees. So what we do is we just transform them into A dash, okay, and then B to B dash using the formulas. So that is, instead of moving Q directly from A to B, it is moved from A to A dash to B dash, and B dash to B, so that only one variable is changed at the time. This makes the line integral a lot easier to evaluate. Thus, we can say minus W over Q is equals to minus 1 over Q integral of W, work done from A to A dash, plus W A dash to B dash, plus W, work done B dash to B. So we can put all these formulas in the integrals, and we can find out value. So all this is solved here, and in the end what we need to find is we need to find W, so work done. So the work done will be equals to 28.125 microjoule. There's another method which is since V is known, this method is a lot easier and very short as well. W is equal to minus Q, and we know that we have to transform or move from Q from point A to B. So we can say A to B, integral of A to B E dot dl, which is equals to Q into V A B. Okay, so we can transform that V into Q into VB minus VA. So when we have VB minus VA, we know the values, and we put the values, and the same answer will be calculated. So that's all for today. Thank you, and we'll come back with the next lecture soon. Thank you very much.